Welcome to today's lecture in GR. We have, in the last few lectures, learned to express the curvature numerically, or actually to quantify it. And the object, the mathematical object that describes curvature was the Riemann curvature, which we called R. Actually, I wanted to have a black color here, R. And we have seen that's indeed a 1-3 tensor. That's the 1-3 tensor field. As I said last time, I will probably often just call them tensor, but they're always tensor fields. And in components, because it's a 1-3 tensor, we could write I, J, M, and N, for example, which shows that there is a lot of data in this tensor. There are many actual coefficients, and all these coefficients are actually needed, because what we have seen towards the end of the last lecture is that you could interpret the coefficients as follows. Take a vector oriented into the J direction, that's the second index, the first lower one. Move it in a loop defined by coordinate lines M and N. So you go along M by a certain amount, along N by a certain amount, back in minus M and back minus N direction. And then you ask yourself, how much does the resulting vector differ from the original vector you started with in the i's component? You see, you need all these indices to express that, and that's what this tensor says. At the end, it's also proportional to the area of that loop. So maybe you remember that we said that this holds to second order. This was the lowest order that was relevant. And in that order, we had essentially taken a derivative to the lengths of these transitions that we make along the coordinate lines M and N. We called them U and V. And therefore, the full expression for the change of the vector was this curvature coefficient times U times V. So the larger the area you encircle, the larger the change of the vector. And of course, it's also proportional to R itself. One other object that we may immediately define now is, so maybe I should have written down the name again. So this was the Riemann curvature, because there are different ways of measuring curvature. We will see things like Gauss curvature and so on. For the moment, we will just define one additional object, which is the Ricci curvature tensor. That's a 0-2 tensor. So let me write here the name, Ricci curvature tensor. It's again a tensor field, of course, so it's defined everywhere, but if I look at it at a particular point, it's of course a tensor. And remember, we had to do actually quite some work to show that R, the Riemann curvature, is indeed a tensor. Now the Ricci tensor is defined directly via R, via the Riemann curvature, just by taking the trace over the first and third component of R. So in coordinates, this can be expressed very easily. Namely, we could just write the Ricci curvature has, of course, now two components. I call them J and I think the second one should be an N. And because it's the trace of R, I can write it as I, that's the first component I trace over, then J I don't trace over, then again the one I trace over, which I have to label with the same index, and then again N. Okay, so why do I tell you that? So of course, I could define different objects. I could take other traces. It turns out that this trace is a non-trivial trace. Because of symmetries, it could happen that certain traces also just result in a 0 tensor. This is not the case for this particular trace. So the Ricci tensor is a non-trivial tensor, and it's certainly a tensor because we have seen that the trace of a tensor is again a tensor. And the reason I I introduced this particular Ricci tensor is because that's one object we could already use to express Einstein's field equations, at least in the case of a vacuum. So what we will see later more generally is that the curvature will depend on the matter in space-time. However, if there is no matter in space-time, we can already still express an equation. So the Einstein field equations, which we will treat later, but this is kind of an outlook, just to keep you motivated and to make sure you already now see the connections between the objects we are introducing and the physics. This Einstein field equation in the case of no matter in the universe. So it's in the same way as when you do electrodynamics, you could look at the Maxwell equations without sources of the electromagnetic field, and they already have interesting solutions. For example, the wave equations are solutions of that, and therefore it's interesting to look at the Einstein field equations without matter. And there they are essentially the statement, they're corresponding to the statement that the Ricci tensor is equal to 0. So last time I already told you that in space-time, one of the postulates is that the torsion is 0. Now we have this additional statement that the Ricci tensor is 0 whenever there is no matter at the point where I evaluate the tensor. So you should see it that way. It's a tensor field, and wherever there's nothing else than just, wherever there is nothing, neither an electromagnetic field or actual matter, like particles, we can set this to 0. Just to ensure that this is not overinterpreted, this does not imply that R is 0. So the Riemann curvature is not necessarily 0, even in places where the Ricci tensor is 0. So if you consider the gravitational field in vacuum, then what we know from that is that its Ricci curvature is 0 at that point, but not necessarily the Riemann curvature. That's something you should keep in mind. And again, it's maybe as an analogy, if you look at the electromagnetic field equations, of course, the source terms in the Maxwell equations, the density of charge or the current, they are 0 in the vacuum, but nevertheless, you could have electromagnetic waves. In the same way, we will actually see that even if this is 0, there can be an R, which is non-trivial, for example, corresponding to gravitational waves. So that's one example where we have exactly that. So there could now be, if you are in free space, somewhere away from Earth, where there's no matter, you could still have that, and that corresponds indeed to gravitational waves crossing us. So with that, we have now actually fully introduced one of the objects that is highly relevant, that essentially describes the geometry of space-time. And like, again, in electromagnetism, we have to do two things a priori. We will later see that they can kind of be combined in an elegant way by action principles, but a priori we have two things we need to consider. One thing is we should ask, or in electromagnetism, we ask, how do charges and currents influence the electromagnetic field? So what's the dependence of the electromagnetic field on the charges and currents? And that will be the Einstein, in the gravitational case, these will be the Einstein field equation. So this is the geometry here. And we will later have on the right-hand side some source terms. Actually, we'll also slightly have to modify the left-hand side, as we will see, to make this fully general. But this is the correct statement in vacuum. But on the right-hand side, the main change will be that we will have source terms. Source terms are just the stuff out there in the universe. This doesn't have to be matter in the form of particles, could also be electromagnetic radiation. So that we will have to introduce later. So that's one thing. But in electromagnetism, we also do something else. We ask ourselves, again, how do the electromagnetic fields, again, influence matter? For example, charges. And this is the Lorentz force in the electromagnetic case. And in the Einstein, or in the gravity case, we also have to ask the question, how does the geometry of space-time now influence matter moving through space-time? So in other words, how does a particle feel that geometry as it moves through space-time? And in a way, we have already done that informally. I told you, for example, if you have a gyroscope, which is like a test particle in the electromagnetic case. So a gyroscope is something that feels the geometry of space-time. And I told you that a gyroscope would then be transported according to what is the parallel transport. And the parallel transport is, of course, connected to the, in particular to R, to the curvature of space-time. So we will have to understand more precisely if we have a space-time with a certain geometry expressed by a Riemann curvature, or more generally by connections, how does the physics look like there? How do particles move? How does a gyroscope move? Maybe this is also just an opportunity to come back to a very good question that was asked, I think 2 days ago, about and the question was, if I have the curvature, the Riemann curvature, does this determine the connection? For example, the parallel transport. Of course, it doesn't actually, it can, of course, not determine the gamma symbols, because the gamma symbols also depend on coordinates. But the question could be, if I know R and if I have a set of coordinates, does this completely determine the gamma symbols? I didn't have an immediate answer last time, and indeed the answer is a bit complicated because there are various conditions, but a very rough and more precise, still more precise answer than I gave last time, where I gave essentially no answer, is that this really depends on the dimension. So if we were in a two-dimensional, I mean, you shouldn't say space-time. Space-time isn't two-dimensional, but let's suppose we just look at a two-dimensional manifold. We can ask this question, if you give me R, can I determine the full geometry of that, meaning the gamma symbols? And the answer there is no. And there it's relatively easy to see why it has to be no. The reason is that R, the Riemann curvature, has lots of symmetries. We will later see them. You have already seen the Bianchi identities and so on. And there are certain symmetries on the change of the indices. And if you consider all these symmetries, you will find that in 2 dimensions, there is essentially only one value left. So this whole curvature is expressed by one single value. Whereas for the gamma symbols, you have much more degrees of freedom. So the curvature cannot, in 2 dimensions, determine the gamma symbols. So there the answer is no, it cannot be. So the curvature is not enough. However, in higher dimensions, in 3, and of course in our relevant case of 4 dimensions, it's actually the case that from R we can get the geometry, at least if we look at manifolds that have a particular connection coming from a metric. This is the type of connection we'll introduce later today. So in this case, we will be able, except maybe in pathological cases, to start from R. So someone gives you just the curvature and you could essentially determine everything you need to know about the geometry of space-time. Okay, that at least partially answers, hopefully, that question. As I'm just about to answer questions, I should also make maybe a remark about something I said last time. I said last time that we can essentially determine experimentally what the connection is. But when I said that, we already implicitly made the assumption that the connection, which is, I mean, remember the connection is essentially the definition of a parallel transport operation. So the connection was formally defined by an operation tau that tells me that if I take a vector, how does this vector move along, if I move along a path? And we were implicitly assuming that this mathematical object, the connection, would correspond to how a gyroscope moves in space-time. Of course, at the end, we want to say something about physics. So it's natural to say that we use this parallel transport to actually express the physical fact, namely how the direction of a gyroscope changes. So this is something we assumed, and this has to do with this coupling between matter and geometry. That was already an instance of where I used somehow a statement about how matter, in this case a gyroscope, couples to the geometry. So it couples, or it takes into account the fact that space-time is curved. And that's via this parallel transport. I should add that there are actually other ways to think about the connection between the abstract or the mathematical manifold that we have, the four-dimensional manifold, and physics. And the usual thing is that we do it in, I will present the standard way in this lecture, but there are actually different ways to make this connection. And if you go along such a different route, you may find quite interesting alternative representations of general relativity. For example, you could then find a representation where you express all the interesting information about what we now kind of capture by the curvature. You put that into the torsion. So, of course, then also matter couples differently to the geometry, because the way you define the geometry of space-time also has an impact again on how the geometry influences matter. But I just wanted to say that there are alternatives. So you may, if you look at even modern literature in research, or in particular modern literature in research, people are asking themselves, are there alternative formulations? And there are such alternative formulations. Of course, in this lecture, I will just stick with the standard one. And in the standard one, we have this coupling of parallel transport to the gyroscope. We have torsion being equal to 0. And we have this form of the Einstein field equation, at least in the case of water. But now let me go more into the question, or at least prepare the ground for us to answer the question, how does now the geometry again influence physics? And for that, we have to remind ourselves again of the equivalence principle. The equivalence principle states that if we are in a small enough lab that is free falling, then the physics behaves kind of, maybe colloquially speaking, in the normal, usual way. And that's something I would now like to express mathematically. So what could that mean? That we say the physics just, we wouldn't notice that we are in the gravitational field. We are just in a free falling lab and everything behaves as if we were just in, let's say, far away from any gravitational source. And the way to express this is to introduce particular coordinates, because in a way the choices I can still make if I'm freely falling is what is actually my reference. And being freely falling corresponds to a particular choice of a reference. And the reference is, of course, connected to the coordinate system. So the claim that we will just see in a minute is that at any point in space-time, we can choose very nice coordinates so that things look as if we were more or less up to first order. And I will make precise what that means in just usual Cartesian coordinates. And in Cartesian coordinates, we understand the laws of physics very well. So the point of this is that we can, at any point in space-time, still go to this simple coordinate system, express the physical laws we are already familiar with, for example, the electromagnetic laws, the Maxwell equation, and then from that on translate them to any other coordinate system we wish. So that really corresponds physically to go to this free-falling lab, do the experiment there, and then ask ourselves, how does it look from the viewpoint of another coordinate system? And you probably remember the example I gave at the very beginning of this lecture, where we had the free-falling elevator, which was just a trick to find out whether light is bent as it passes a gravitational potential, or as it is going through, for example, close to the Earth's surface. And that was exactly this. That's exactly the trick we now want to formalize. So we go into the free-falling reference system, and formally this is just called, we introduce so-called normal coordinates. That was now a long motivation, but it hopefully makes it clear to you that this is quite a kind of useful concept in particular to get some physics intuition. Whenever we talk about coordinates, it's not something that is absolutely necessary, but in this case, it's something enormously useful to actually connect things you already know about physics to how it behaves then in general relativity. So just a last remark before I start with the technical part. In principle, when you introduce GR, or let's suppose you have learned everything about physics except for GR. So everything took place in the arena of flat space-time. Then if now someone like me tells you actually space-time is curved, you would have in principle to redo everything you did so far in physics, because it's almost any statement you make in physics, of course, at least implicitly refers to the structure of space-time. Of course, you probably never make this very explicit because you just assume space-time is as usual, like parameterized as you do it in electrodynamics and so on. But now, if this is no longer the case, you have to go back and ask yourselves, how do the laws now look like in this more general situation? And that's essentially what is achieved via this move to the normal coordinates. So that's a tool, a device that helps us to do that step. So what are they? So when I talk about coordinates, I'm of course talking about a chart. So a chart, UX, is called a normal coordinate chart at P. And this is very important. So it's just 3 letters, but it's important that you remember that it's at P if the following holds. If at this point the gamma symbols disappear. So you probably can already guess why this is nice if they disappear and why this corresponds to a very useful coordinate system. Because remember, if you take, for example, a covariant derivative, and the covariant derivative is really the thing that is physical, that's coordinate independent thing. If you take a covariant derivative, then this is related to just the usual partial derivative and in a linear way, but we have a correction term, and the correction term is essentially the gamma symbols. So if the gamma symbols are 0, this correction disappears, and we can just treat any covariant derivative as a normal partial derivative. And now you probably see the connection to Maxwell equation. You can now say, in this coordinate system, I can just work with the Maxwell equations in the usual way, just the normal partial derivatives. And then, however, I treat them, let's say the procedure would be as follows. You say, okay, in this coordinate system, you don't need to make the distinction. So you just take the Maxwell equations as they are. But now you have to remember that, of course, if you write down the Maxwell equations and if you write down partial derivatives, you have written down something which cannot be physical because a partial derivative is coordinate dependent. But now in normal coordinates, you can just replace the partial derivative by a covariant derivative. And there are no additional terms occurring because all the gamma symbols are 0. So you have immediately turned this non-physical equation, which is coordinate dependent, into a physical one, which is no longer coordinate dependent. And now you can move to any other coordinate system. And of course, you have now transformation rules. So you can transform these Maxwell equations into another coordinate system. And because you have replaced everything by covariant derivatives, things will still transform correctly, or when you transform them, you still get the same equations just expressed in another coordinate system. So this is the way to, very simply speaking, to generalize these things. There are, of course, a few subtleties that will play a role, that will become important, in particular when we have, for example, things happening not only at one point, because it's important here that it's only at the point, so we do that at one point. And why do I stress this one point so much? The reason is that we can prove the following claim. If the torsion T, so T is now not an arbitrary tensor here, it's the torsion tensor, is 0, then at any point, so I don't, by the way, always repeat that we are working with differentiable manifold and so on. So that's always underlined. So the torsion of the differential manifold, and the point is an element of the differential manifold. Then there exists, for all points, there exists normal coordinate. There exists a normal coordinate chart. At P. Okay. Now, the claim is kind of nice because it tells us we can always do that, but it's also weak because it only tells us that we can do it at one point. So for any point, there is potentially a different coordinate chart. So there's not one coordinate chart that has gamma symbols everywhere. So in other words, we can make the gamma symbols disappear at any desired point we want, but only generally at one particular point. And then if we want to make them disappear at another point, we need to, again, move to another coordinate chart. So this is a claim that I would like to briefly prove, because I think the proof is kind of nice and also simple enough to write it down in relatively short time. By the way, regarding timing, I have today a slight collision with time. I should give a talk in Israel. Now, this is very easily possible in this virtual world today, but the talk starts exactly at 1:30. By the way, you're very welcome to attend that talk if you like, and if you're interested in quantum computation. But for that reason, I will have to end the lecture at 1:20. So my suggestion is that I just work through the break, so that we essentially lose very little time. So then the total time of the lecture will still be 80 minutes, and you can then take a longer break at the end. I hope that's fine for you. If not, yeah, I cannot do much about it, but then you may just watch the recording after the break or something like that.
Can I ask a question?
Yes, of course.
This claim is basically the reason that we talked about in equivalence principle, that you always say in a small, small room. This.
Yes.
I mean, yeah, the locality comes from this claim.
Yes, right. So, of course, I mean, that's a very good question. How does this now relate to small? So in a way, you could say it relates to small because I'm just doing it at one point. Now, that would not be very satisfactory, but we will later come back to that claim. So actually, at the moment, we cannot even talk about what small really means, because there's still one missing element, which we'll introduce just, I think, after that proof, more or less, or maybe a bit later today, which is the metric. The metric is the thing that will allow us to, for example, measure how much time passes between two events, and also then to measure distances with that. And we will return to normal coordinates, and then I will be able to tell you a bit more precisely where they are still useful. And it turns out that they're, of course, useful in a small region around that point, up to a certain order. So you should think of this like, I mean, another way to think of it is at the gamma symbols there. There will later be, okay, that's just for, maybe I'll explain this later, but in more detail, but the gamma symbols will kind of include first derivatives of the metric. So up to first derivative, in other words, to the first order in a Taylor expansion, things will look as if I was in flat space, more or less, but only to first order. And yes, I hope that just gives you an outlook. So we will come back to this. Okay, for the proof, I assume just that I have an arbitrary chart in the same region. So let this be an arbitrary chart. Of course, I still assume, I mean, the region U should include the point I'm interested in. So maybe I'll write that, such that P is an element of U. And I also can always assume, without loss of generality, that I shift the labeling of the coordinates in such a way that the point I'm interested in has coordinate value 0 in all coordinates. And that's, of course, always possible. That's just a translation of the values. And now we construct a new map or a new chart map. Okay, it's very called coordinate or chart map X. That's the one we want. And this is now a construction which just says explicitly what is the coordinate of an arbitrary point Q in U. So what I'm now going to write should be true for any Q that is still an element of the chart. So I construct it in the following way. Essentially, it's like an expansion. I say, okay, to 0th order, the coordinate should just be the same as the corresponding coordinate in the tilde coordinate system. This was the arbitrary one I started with. And then I say, there should be a small correction to it. And the correction is actually to quadratic order. And the correction I give explicitly, the correction is just given in terms of the gamma symbols, or more precisely, the symmetrized ones. So remember this round bracket means I symmetrize things at the point P of the tilde coordinate chart. So the tilde chart is, of course, just an arbitrary chart. So it has also arbitrary non-vanishing gamma symbols in general. And I just write them down here and multiply them with the coordinate in the R direction of the point I'm interested in and the coordinate in the S direction I'm interested in. So this is just a receipt. How do you determine the coordinate of a particular point? Take the point in the tilde coordinates and multiply the coordinates with the gamma symbols exactly in the way it's stated here. And now the only thing we have to verify is that the gamma symbols of the new chart map of this one disappear. So we just will now do a little calculation. How can we determine the gamma symbols of the X chart? We can just transform the gamma symbols of the X tilde chart into the X chart, and we know the transformation rules. But the transformation rules, as you probably remember, depend on expressions of this form. So we usually have derivatives of the chart transition function or chart transition maps. So they involve terms like this. And so it's useful as a preparation for the rest of the proof to briefly calculate these terms. So what's this term? What's
Sorry?
Yes?
Question. Is it clear that this new chart map is actually bijective?
That it's injective.
Well, yeah. Because, I mean, it could be that this correction term makes, like, 2 points end up on the same place.
Yes, that's actually a good point, which I didn't now think about in this presentation. However, it's not a worry for the proof because I can just choose the U to be sufficiently small. So, the claim is just there exist normal coordinate charts and the U can be arbitrarily small. It just needs to include P so that this is still well defined. And it's clear that if I mean, these gammas could be arbitrary as long as they don't diverge. I have here small numbers and I can then multiply it with these. I mean, these terms will be very small, so I don't run into a problem. But that's indeed something one would have to verify carefully. Maybe what we can do is actually, you can also invert it and then see explicitly that you can indeed express xi from x tilde, but and in a small enough region, this would always work. So maybe the answer to your question is yes, that's indeed a concern, but for small enough values, it's not as can be. But I will not go into that further. Maybe we can discuss it in, let's say, the break next week if you're interested in exactly the proof of that. So that
it's fine.
Thanks. Okay. So, I mean, by the way, that's generally always a trick in a way. I mean, it's not maybe it's not really a trick, but it's a way to avoid these problems. Just look at things in a small enough region. And that's what we do here. So if they now are, we can look at this, this derivative, and the first term comes from this. So if I take the derivative of this whole thing to the variable x tilde r, then of course I get from this term just a delta function, because it's only relevant if I is equal to r. Then from the next term here I have a square essentially, and that's like a quadratic function. So I get a factor of 2 which cancels with the 1/2 here. And so when you do this derivative to r, you will find, of course, that the prefactor remains. That's just a constant. Here was a p. That's not depending on the part. And then, because it's a square, just one, if I take the derivative to r, the s remains. Okay, that's something, that's just standard algebra. You can probably easily verify this thing. We will also need second derivatives. By the way, maybe just as a, actually here is now the answer to the previous question. Almost there. I mean, if this thing is not, if this matrix, if you like, is invertible, then indeed the chart map or the transition map is invertible. So you just have to check whether this matrix is invertible. And then now you see this is an identity matrix. And if this x is sufficiently small, then this term cannot make this identity matrix non-invertible. There would have to be entries here which are at least of order 1. But as I said, this x can be, if this is bounded by some small value, if you bound it, then this cannot happen. So this should actually completely answer the question that was just asked before. Okay, now we also need second derivatives, which are, I just write them down here, at the point q. And here, of course, the delta function disappears because it's a constant. And what remains is just the derivative of the second term. That's very easy because it's a linear term. So it just, what remains is really this prefactor here. Okay, now let's just move on to a new page and we'll have our previous calculations here. So what we can now do with that is to indeed express actually, I do it the other way around. I express the old gamma symbols, the ones that are not 0, in terms of the ones that should be 0. This is just easier to do. And as you will see, this will still allow us to verify that the gamma symbols are 0. So what I have to do is to now just write down the chart or the transformation rules for gamma symbols. And if you remember, the gamma symbols don't transform like a tensor. However, they have still one component in the transformation rule, the one I'm currently writing, which follows the same transformation law as a tensor. So what I wrote down so far is exactly the transformation rule for a tensor. But of course, now you see, if the gamma symbols were tensors, then if they were in one chart non-zero, it would not be possible to make them 0 in another chart, because the fact that a tensor is equal to 0 is a chart-independent thing. Because, you know, saying that a tensor is not equal to 0, I can say without referring to a chart. That's just a property of the map, the tensor understood as a map. So it's crucial here that the gamma symbols are not tensors, otherwise I couldn't transform them into a coordinate system where they are 0. So this second term that appears in the transformation rule plays here the crucial role in this whole proof. And this second term is the one that involves the second derivatives that I just calculated. So far I didn't actually do more than just copying from earlier the transformation rule. But now we just have to insert things, and this is very easy, because as you can probably see, at the point P, so by the way, I evaluated them here at an arbitrary point Q because I needed to take the second derivative, and I can only take the second derivative of this thing here if it's evaluated also in the neighborhood of a point P. But now I'm only interested in this here at the point P, because there are only P's appearing here. I'm only doing it in P. So at the point P, this x tilde is just 0. So the only thing that remains is this delta function. So in other words, these coefficients are just delta functions, delta JR, and this is delta KS. And the first one is one that we didn't calculate because it's the inverse. But of course, the inverse of a delta function, I mean, we know that the inverse is really just to be understood as the matrix inverse in this case. So the inverse of a delta function is again a delta function. So therefore, this is just a delta function of ui. So they're all delta functions. And of course, the same is true for that one. I'm not going to write that. That's the same as this. And this term here is the one we also calculated. That's just that thing. So this is just gamma tilde at P with the coefficients I and symmetrized RS. Okay, now you probably see that we are almost done. Let me just rewrite this by evaluating the symbols. So these delta symbols at the beginning just allow me to write the thing here on the right-hand side with the indices U, R, and S at the point P. And then the second thing, because this is again the same delta function, I can identify the U with the I, or the I with the U. So what I get is here comma U R S P. Now remember that we assumed in the theorem that it's torsion-free. Torsion-free means that the symmetric gamma symbols are or that the gamma symbols are anyway symmetric. So I can as well just drop the bracket here. And if I drop the bracket, then we have here and here just exactly the same expression. And so that can, of course, only be the case if gamma U R S P is equal to 0. And that concludes the proof. So we have indeed constructed a coordinate system in which the gamma symbols, all these appear at that particular point that we design. And for any point, it's a different construction, because you see very explicitly the construction depends on the point P. We have made here this assumption that the original system coordinates from which we started disappear at 0, and then we made this construction by kind of an expansion around that in some way. Okay, let me now immediately continue with something that is not directly related to that, but we will immediately later relate it. And this is the notion of straight curves. This is an extremely small section. It's essentially just consisting of a definition. A straight curve, you have probably already seen it, but I just wanted now to really introduce it also formally. Gamma is a curve, of course. Certainly a curve if it's a straight curve, such that the velocity vector of the curve at any coordinate point U is just a parallel transport of the velocity vector of the same curve at another coordinate point T when I transport along the curve. So, okay, I'm not even sure it's useful to draw a picture because it's so simple, but maybe still pictures sometimes help. So this would be the curve gamma. And the point is that I look at a velocity vector here. That could be the velocity vector. That could be gamma at T. So it's the coordinate. It's the point for parameter T. And then there is here, of course, a vector gamma T. And now I may parallelly transport this vector along the curve. Now on a manifold that doesn't, I mean, now I draw it on a flat iPad, but of course this could be on a sphere and so on, and then it would not look as trivial. Here I have the new vector at the point, parameter point u. And now the curve is straight, which is by the way not the case for this curve, of course, because, okay, actually this is a bad drawing. Let me slightly revise the drawing. So of course this is a tangent vector to the curve. So it would look like this. So if I had only these two that I've drawn here, they would indeed be parallelly transported. But of course the tangent vector here looks different. And so this condition would not be satisfied for all u and t on this diagram. Of course, that's diagrammatic, and we know that things may look curved even though they are not, and so on. But I guess you get the point here. So the point is, straight is defined relative to the parallel transport. So I think I used this notion of straight already earlier when I had some examples that we move straight along certain lines. But I think this is really now the only way you can, up to now, we will later see another way, but up to now, this is the only way we can really express what straight means, because we have no other structure. The only thing we know is what does it mean that a vector stays kind of aligned in the same direction. That's the parallel transport. That's the structure we impose. And now we just say if the direction of how we walk always stays in the same direction, then that means we walk straight. That's kind of intuitive. Now, this condition is, of course, equivalent to a differential condition, because we know that the covariant derivative just corresponds to the parallel transport in an infinitesimal region. So remember, it was just defined as via that by making u very close to t. And so we can as well express it as saying we walk along the curve. So that's the derivative. We take the derivative in the direction of the curve of the vector of the curve. So you see the vector appears twice. It appears here because here it defines in which direction we go. And here it says, what is the thing that shouldn't change? So as we walk in a certain direction, that direction shouldn't change. And so this thing actually is not completely well defined. So this definition is kind of really clean. Here, you would in principle have to extend the vector field, which is on the curve. I mean, this vector field is only defined on the curve because it's the direction vector of the curve. And a little bit next to the curve, there is no direction vector of the curve. But the covariant derivative really acts on a vector field. So in principle, you should think of this as the extension of the vector field defined by the curve along the curve to the whole manifold. But it turns out, and you see that from here, of course, the other values of the vector field are not really relevant. But formally, for the definition, for this to be well defined, you would need a vector field that is extended away from the curve. Anyway, that's just a technical subtlety, because once you have seen this definition, you know that it's sufficient to just consider the vectors on the curve. Okay. Now there's another very small chapter, which is parallel transport in coordinates. We have, of course, already seen parallel transport. That's exactly what this tau did. The tau is the operation that parallelly transports a vector, and that was our basic notion. We didn't define it further. We just said we are given such a parallel transport with certain properties. And now we use the parallel transport to define what a straight curve is, but now we can also ask ourselves, how does a parallel transport really look like if we write it down in coordinates? So remember, we can essentially define the parallel transport, which was defined really by taking a vector at one point and transporting somewhere else. We can also look at things in the opposite way and thus say we already have a vector field and ask ourselves, does it correspond to something that was parallelly transported? So that's why it's, I write this in a slightly different way than before. So a vector field X is parallelly transported that's a term along a curve gamma. Curve now doesn't need to be straight, an arbitrary curve. If, this is also now very intuitive, if I walk along the curve and look at any parameter point t and look at this vector field, it doesn't change. So it's the parallel transported vector field is really one that doesn't change in the following experiment. So I always had this gyroscope experiment. Now think of the space or space-time being filled with vectors. There's a vector everywhere where I walk, where I pass by. And so this is this vector field X. So it's really a field of vectors. Now it's called parallelly transported along the curve gamma if physically the following is the case. I walk along the curve gamma, I take again this gyroscope with me, align at the starting point the gyroscope with the vector that I find at the starting point. That's one vector, xp. And then I just move with my gyroscope and check at every location where I pass whether the vector is still aligned with the vectors I find at this location. So wherever I pass, I find new vectors and I check whether my gyroscope is aligned with these vectors. And if this is the case, we have mathematically this condition fulfilled. So this is kind of the change of this of the vector field X relative to my gyroscope, which is implicit to this derivative, doesn't is zero. That means it doesn't change. Now, as I said, I wanted to go to coordinates. And in coordinates, I could write down the following. So here I have, again, this derivative, covariant derivative of the vector field X. And now I want to know the ith component of that. And maybe I should briefly remind you of something here in a little box, just to make sure you still are aware of that. That, of course, the vector, the velocity vector along a curve at the point t, or at the parameter value t, we sometimes write as an abbreviation as gamma dot k d to the d xk. I think I already introduced that at some point, this gamma dot notation. And we have shown that this is indeed the case if we define, so this equality holds if we define gamma dot k just as d to the dt gamma k of t. So that's a very intuitive thing. It says the following. If I look at the time derivative, that's what this dot means according to this definition, of how the k component, so this gamma k just means the xk value, the k component of the curve relative to a chart. That's all in the chart because we are now talking about coordinates. So I look at the time change of the coordinate, of the k's coordinate. And now the point is that indeed the direction vector in components just corresponds to, or has coefficients. These are the coefficients and these are the basis vectors, has coefficients which are exactly these time derivatives. That's something that is extremely intuitive if you think about the flat space. That's essentially how you would define a velocity vector or a direction vector. And we have already shown that this is indeed the case. And it's also very easy to verify. It's just a one-line calculation using the definitions. Now, because of that, we can, or okay, now I use something else that we already did. This is not something you should, or this is something you should really remember, namely, how does the covariant derivative, remember this is something we even sometimes wrote as Yeah, okay, no, I don't write this. So maybe remember the semicolon notation, which we introduced in this context. But what I said is that the covariant derivative can be expressed in terms of the partial derivative, which is denoted with a comma, plus the correction terms. Remember, that's also part of what I used in my motivation before when I said that in normal coordinates, the partial derivative corresponds exactly to the covariant derivative, and the partial derivative, of course, agree in the case where these gamma symbols are zero. Because if the gamma symbols are zero, we really have the formula you know from analysis. It says that if I want to take the derivative of a vector x in the direction of gamma, then I just multiply this direction gamma. So remember, these are the coefficients of the direction vector. That's what I said here. So these are the coefficients times the derivatives in that direction of xi. So that's what you would say what it means in standard analysis to take the directional derivative of xi, of the i's component of a vector field. And that's indeed true if the gamma symbols are zero, that this formula applies. But with gamma symbols, we have this modified formula that I wrote down here, which we also derived a bit earlier. Now we will introduce another notation, which is quite useful and also intuitive. Before I use the notation, let me make you aware of the fact that what this means here, to take the gamma, yeah, maybe I'll have to do a small calculation just to be sure that I don't jump too much. So if I write this out, what is here without the comma, but with proper full notation, then I have here partial derivatives. So that's just really the same thing. That's the comma notation. Now, of course, this object here is again the velocity vector. That's what I wrote here. So I could also write this as equal to the velocity vector of the curve applied to xi. So a vector can be applied to a function, and here I'm just applying it to the coordinate function of the vector field x. And now you also know that a vector applied to a function, a vector along a curve, means by definition, that's the definition of the velocity vector, that I just take the time derivative of the function, which in this case is the function xi, at the point of the curve. So along the curve. So I walk along the curve and take the derivative. That was something we did at the very beginning when we introduced velocities and directions. And now comes my notation. This thing, which is now a time derivative, I will just also denote with a dot. I will just call it xi dot without anything else. That just simplifies our lives, because I can now write this in a nice form, this whole thing. So I can now say that the condition for parallel transport, so this equality that this is zero, is equal to x dot I plus, so that x dot I took care of this whole thing here. Then of course the gamma dot has to be applied to the second term as well. I will do that. So the second term consists of gamma ijk, xj, and then still the gamma dot from before the bracket has to be applied, and this whole thing should be zero. So that's the equation for a parallel transport of a vector field. So later we'll often have to evaluate or find out whether a vector field is parallelly transported. So that's really what it means. Now, of course, it in particular occurs when we ask the question of whether we have a straight line. Because if you look at this condition here that I wrote down for parallelly transported, then of course I could have said, if you compare it to this one, that a straight line is just is equivalent to a line, to a curve, such that if I transport its own velocity vector, so I take x to be the velocity vector of the curve, if I transport it, then it's parallelly transported. So in other words, for straight lines, we just have to set x to be equal to the velocity vector. So in words, I could say a straight line is a line whose velocity vector is parallelly transported. And in components, this now means that it's this. Because remember, the gamma dot I were just the components of the vector, and xi are, of course, by definition, the components of the vector x. So now I can insert that here. So x is now gamma dot I. So therefore, the condition for straight lines now reads in coordinates as follow. I just copy essentially that condition. What does this give me? I get a double dot because I insert the gamma dot as x and take again the dot. And then I have the gamma symbol, I, j, k, gamma dot j, gamma dot k equal to 0. That's again a condition you should kind of learn by heart, or at least put on your piece of paper of things you should once in your life learn by heart. This is the condition for a straight line on in an arbitrary coordinate system. By the way, I already tried to encourage you to attend the exercises on Tuesday. I again repeat that, so please attend the exercise classes and do the tutorials. There's a very nice exercise sheet that you can solve today where you actually calculate these gamma symbols even for the flat case, and you will see that the gamma symbols are not necessarily 0 in the flat case. They're just depending on the coordinate system you choose. But once you have all these techniques, you can now very easily calculate a straight line, for example, on a sphere on the surface of Earth. That you also do in the exercises. You find the gamma symbols for that, and once you have the gamma symbols, you can now have explicit expressions for straight lines, straight in that sense. So what does a straight line mean on the surface of the Earth? It's really when I walk straight. Of course, seen from the outside in the three-dimensional space-time, it's not straight, or in three-dimensional space, but on the surface, it's straight exactly in that sense, that the vector of my direction is parallelly transported. That's what it means to walk straight on a surface that is itself, as viewed from the outside, potentially curved. Okay, so I think that gives us a lot of tools into our hands, and but we can now make one further step even closer to what is needed physically to do GR. But because there is no break today, let me nevertheless ask whether there are any questions up to this point. I don't see any or hear any. Okay, so I'll write in the meantime already the title of the new section, and you can of course still think about questions and interrupt me whenever you like. Pseudo Riemannian manifolds. What's this? So far we have introduced the following structure. We had the differentiability structure, and then we have introduced this parallel transport, which kind of defines in some way some geometry, tells us what it means that things remain straight. And now we will introduce a structure which is in a way containing more information than that. And it will allow us to measure distances, as I just announced a few minutes ago. And distances in space-time, you should always think, or I think it's more useful to think actually of time. They measure, for example, proper time along a curve. So how much time passes. So whenever I talk here about distances, you shouldn't necessarily think of spatial distances. Okay, a pseudo-Riemannian manifold, what's that? Is, first of all, just a differentiable manifold. By the way, one without the connection so far. We will introduce it later again. So we only have the differentiability structure. So that really goes back in the lecture to the kind of a quite early part where we didn't even know what the transport means. So we only have the differentiable structure, and now there will be some additional element. Okay, so the additional element is the following, together with a differentiable zero-two tensor field, which we call G, such that GP, so GP just means the tensor field evaluated at P, so it's a tensor on the tangent space at P, is a pseudo metric on TPM at any P. Okay, now you have to probably remember what we did in the very beginning of the course, where I repeated a bit of linear algebra, and we introduced tensors in vector spaces, on vector spaces. Now we have a tensor, of course, again, on a vector space, namely TPM. And at that time, I also introduced the notion of a metric and of a pseudometric. Now, a pseudo-Riemannian manifold is one where at any point we have in the corresponding tangent space such a pseudometric. So what is a pseudometric? Just a very short summary. It's, of course, as said here, a 0-2 tensor then at every point. So it takes two arguments and it's symmetric in the two arguments. So this thing holds and it's non-degenerate. And maybe a very abbreviated way to write this. We did it much more in detail last time, is to say that if I look at the tensor or the covector that is generated by just introducing only one element, I only put in the first argument and leave the second open. Then the remaining object is, of course, an object that eats still one vector. It still can eat this thing here and spits out the number. So this thing is a covector. And now the point is, if this covector is 0, then it must be the case that x was 0. That's what non-degenerate means. So in other words, for any non-trivial x, this object here defines a non-trivial covector. Now the pseudo just means that we are more general than what is usually understood as a metric in mathematics, which is the same as what I wrote here, but instead of the second condition, you have positive definiteness, which means that if you insert the same vector twice, you get a value strictly larger than 0. We don't require that because space-time doesn't have this type of structure in it. We need this more general thing. And because we always need this more general thing, I will not always use the word pseudo. But from now on, when I talk about the metric, I mean a pseudometric. Okay, there were quite a few things that we introduced when we talked about the metric. And in particular, the metric defines at any point of the manifold. Therefore, the metric tensor or the metric at that point, a lowering operation. We are also introduced then, we call them musical B, and also an inverse, which we denoted by a sharp. Maybe, okay, I don't want to now go into everything we did already, but just for the lowering operation, it may be useful to have it here on the board. It maps any vector to a covector, which is then denoted by x with this little musical b. And this covector is the covector I just explained before, the one where we just insert one argument. So, I mean, what this means is just that xb, if I now insert indeed a y, gives g of x, y. Just to be clear what this dot means. Now, the reason why I wanted to repeat that is that we can also define a 2-0 tensor field. So the metric was a 0-2 tensor field. And now we can at any point define a 2-0 tensor, and of course with that we have a 2-0 tensor field, as we do it at every point. And this should be defined as follows. So it's called G inverse for reasons that are maybe already clear to you. And it's defined as follows. It eats, of course, two covectors, and the way it outputs a number, or it calculates a number, is that it takes this raising operation chart, applies it to one of the covectors, and therefore makes a vector out of it, and then applies the other covector, in this case phi, on this vector. Just a remark, g to the -1 p is also symmetric. And g was symmetric by definition. So what okay, maybe I tell you why it is. That's so easy to see that it's maybe easier to just write it down than to give some wordy explanation. So if I introduce two covectors, and of course as covectors I can just choose the lowerings of arbitrary vectors, because these are, I mean, we are in finite dimensional tangent spaces, and then we know that the covector space and the vector space have the same dimension, and the lowering and raising operations are vector space isomorphisms. So therefore we can write the arguments as that. And then if you now introduce this just into the definition, which says that apply the first argument, which is a covector to the raising of the second argument, the raised yb is of course just again y, and this is what I get here is now exactly this. So I can write it in terms of g, xy, and g is by definition already symmetric, so therefore g inverse is also symmetric. Now another important notational remark, if you have g inverse and right components, then we will just write Gij without the inverse. Because the G has its components downstairs, the original G, it's a 0-2 tensor, so there's no ambiguity by writing G with upstairs indices. This is always just the inverse metric that is meant. Now it turns out, and this is a simple calculation, that we have actually more or less already done in the vector part, in the first part, in the linear algebra part of the course, that it's, and this justifies the inverse thing, that if I take Gij, the components of this inverse metric, and contract it with Gjk, then I get the delta function. So in this sense, the G is really an inverse matrix. So that the G inverse, the components of the G inverse form a matrix, and this matrix is the inverse to the matrix formed by the G itself. Okay, now the last thing I want to do for today, as I said earlier, I have to leave very soon, is the Levy Levi-Civita connection. And that's something we'll discuss for longer, but I just want to introduce it at this point. Just give the statement, which is in a way the a very important theorem. And okay, it's not only in a way, it's actually called the fundamental theorem of Riemannian geometry. So if you ever invent a theorem, make sure someone calls it the fundamental theorem of something, and then you will probably become famous. For any, so the theorem talks about any pseudo-Riemannian manifold, not only Riemannian ones. I mean, I will later again maybe come back to what the differences are between pseudo and non-pseudo. But for the moment, this distinction is not important because it holds for any. So one should say a pseudo-Riemannian includes the Riemannian because a positive semi-definiteness is implied by the second condition we had before. With metric G, okay, actually it's clear that it has a metric G because that's just how we define it. There exists a unique connection called Levi-Civita connection. Such that it's torsion-free and the parallel transport along any direction v of the metric gives 0. And it's actually given specifically, so one doesn't even say that it exists. It's actually a constructive statement. And of course, the connection is defined via the gamma symbols. And it's given by a formula which, again, corresponds to the set of formulas you should promote to things you know by heart. And it has a lot of symmetries. You probably see it by inspecting the formula. So it's not too hard to actually keep it in mind. So that's the connection. So in other words, what we have done now is to say that instead of just postulating this connection, this parallel transport, we introduce something else, a metric. And I will tell you next week what this metric really means physically in more detail. And then the point is, once you have defined the metric, you don't need to independently now define a parallel transport. There is a very natural parallel transport, namely the one induced by the Levi-Civita connection, which follows from the metric. So it's essentially the parallel transport that leaves the metric invariant as you transport it. I will next week discuss a lot about the physics behind that. There's no time for that today because this will really take extended time. But maybe one thing I should already say, also in view of the exercises, is the following. It turns out that if you look at the Levi-Civita connection and look at straight lines, so remember straight lines are defined depending on the connection, then these lines are also the extremal lines in terms of length. So if you ask yourself, you take the metric allows you to measure lengths of curves, and you take, for example, the longest or shortest curve between 2 points. Then at the same time, this is also the straight line between the two. That seems obvious, like if I take a little rope and pull it and make it shortest, then it's straight. But the statement will be, we haven't proved that yet, but it will be that this is true also in curved space-time. So what we call straight in in general geometry is also in a way the shortest or sometimes the longest path. There will be a lot more on that on the exercises. So again, I recommend them because it will help you to get a feeling for all these definitions. So please attend them. Now, as I think already said now more than once, I unfortunately have to now move to a talk that I give. And some people, because I already had a talk, I think 2 or 3 weeks ago, about something which is very different from GR, but some people know that I'm doing quantum information and computation. People ask me whether they could actually also attend the talks that I'm sometimes giving next to the lectures. And in this case, you are extremely welcome if you want to, if you are not tired now and want to see something about quantum computation. You can now move to Israel for an hour and look at that talk. I just pushed that in the chat. I think this is a link, and the talk will start shortly. I hope for your understanding that I cannot take questions now, but I'll be very happy to take again questions in the lectures next week. Okay, that's it for today. Thank you, and hope to see you next week or in 5 minutes again in this other talk.